Hello, everyone, and welcome to the next part of CP Bootcamp, whatever it is. And today we are going to be covering binary search from the CSCS book. It is inside of here. So, yeah, that's what we're going to be doing today. So, let's get started. So, first of all, what is binary search? Binary search is actually much more than you think, much more than a sorted array. But let's start from beginning. Okay. So, let's say, not this. So let's say we have a array, right? And we want to find an element that is equals to some value 53. How can we find it? To find it, we have to iterate through the elements and see which one is equals to 53. So that would take O(n) time complexity on average. So that's good. And how can we try to speed this up? Okay, so that's the most trivial application of binary search. Now, let's say this array was sorted. So it was something like this. Okay. So this is the array and we want to find 53. Let's say we check this element. Okay. So if we check this element and we know that 7 is less than 53, what do we conclude from this? We know that if 7 is less than 53, then that means these two elements that we have not checked yet are also not equals to our value, because if 7 is less, then they are also less. That means we just need to check this remaining part. So basically, with this comparison, we are able to determine that some part of the array is useless to us, and this is the part that we want to check. So if we do this in a uniform or way, that is, let's try to undo all this. So let's say we are searching for 79. Okay, this time we are searching for 79. If we start from the middle, okay, because we are trying to do it in a uniform fashion, I'll you'll see why we are doing it from middle. If we check that 53, okay, 53 is not equals to 79. That means this entire part of the array is useless to us. And now we can check this part. Okay. Now, obviously, a better thing to check would have been 60, because then we get more part that has been converted to useless. But if 60 was greater than whatever we are finding, right, then less number of elements would have been eliminated. So to keep it a good result, regardless of it is if it is less than or greater than, we check the middle. Now once we have checked the middle, in the step 2, which is color red, we are going to try this part. So let's say we check 101, we know it is greater, so this gets eliminated. And then we have this part of the array, and then we check 60. We know that this is less, so we eliminate this part, and then we have the only remaining value, which is 79, so we get the value. So that's how binary search works. You might have already applied binary search as in many other things in life. So it's a very simple thing, but having a specified algorithm for this is helpful. So this is binary search. Now let's have a look at how to implement this. Okay, so this is our array, right? Let's add some more elements to it. So 5, 10, 11, 88, 4. We have some duplicates too. Okay, and let's just sort this, right? So we have sorted it. Notice that for that property to work, keep going there. Yeah, so it's here. I used to have Excalibur like this. That is why I have a habit of changing. So yeah, now notice that if that property did not satisfy, then if we check 53 initially, and the number 79 could have been here. So we cannot discard this part. So that is why we need it to be sorted. Now we are assuming the array is already sorted. I just don't want to write it in a sorted order because I'm lazy. Now let's implement the algorithm. So first of all, we are going to have two variables, low and high, which will represent our current search space. Okay, so they represent the indices from left to right, which we are searching, and they are inclusive. So 0 is also included and -1 is also included. Now we're going to do a while loop while we have any element, okay, in this range. So what we're going to do, get the mid element, okay, and then what we're going to try to see is if a mid is equals to our target. So what is our target? Target is, let's say, 88. Okay, now a mid, if that is equals to target, then that means we have done it, right? So see out mid and return, right? Otherwise, if a mid is less than target, then that means the left part of our current portion from low to high is useless. So we can just say low is equals to mid plus 1. Basically, this is the array. This is low, this is high, this is mid. If it is less than target, right? If it is less than target, we know this part is useless. So we bring low here. Now, so this happens. Otherwise, the case would be obviously that it is a mid is greater, so high is equals to mid minus 1. And if we are not able to find, right, then what we are going to say is element not found. Now let's try to run this using cph. And all right, why? Let's just break out. Now, I mean, I can do return 0. Oh, F1. So yeah, we found the element to be at 9. Let's print the array for our reference, right? So just printing the array here. And as you can see, 88 is at 9th position. So it is working fine. And this is how I usually do the binary search. I have a low to high. So I have low and high, which are inclusive of the range, and the loop goes from low less than equals to high. Now there are multiple ways. Some people do it like low less than high. Some people do it in different ways. I try to just use this because it is simple to understand and hard to make errors. Now, this another thing, we actually don't have to specifically check this, but we can say that if it is less, right, then we do this. Otherwise, we do this. And then in the end, let's just see out what our low was. Okay. So just see out what our low was. And as you can see, we got the correct element. That is 9. So we can just check if a low is equals to, what was that? Sorry, we don't have to check it like this. If low is, oh, no. So if low is less than n and this is equals to target, then that means we found the correct thing. So element found at low, otherwise element not found. And as you can see, if I do 4, I'll find it at 0, 1, 2, 3, 4. I found its first position, and if I do 6, which is not present, I'll get element not found. Now, why did this work? Basically, if it is less, then so this condition remains correct, right? Now, in the case of equal as well, this will reduce our right part, right? So what will end up happening is we will get low to be at the, so if this is the position where we want where the target is, low will come here and high will come here. So that is one thing. That is also how you can do it. But again, I prefer the former one because that is more explicit. So yeah, that is our binary search. Now let's go and see that okay, this is their method. You can check theirs. This is also like very simple. This is actually the same that we have done. Now there's another way, and that is a little bit different. I'll explain to you the methodology, but I won't really code this because the reason is I don't prefer to do it in multiple ways. I prefer to do it in one way only because that helps to not forget binary search implementation. So what their idea is in the second way is that first if we are gonna binaries so no so we are gonna binary search, right? We are gonna have a step size. So what is our step that we are taking? Initially it's gonna be half of the array, right? So we take half of the it has to be half of the array, right? Yeah. So initially the size of the step is half of the array. So we check from 0 plus the step size. So we check here, and if this is less, right, then that means we want to go to the right more. If it is more, we want to go to the left, right? So now what we can do is try to take one more step, right? I guess we have to take one more step, right? They have done it like while, but so essentially you can do one more step, right? And that step will be here. Now if the condition remains true, then we're going to try to make one more step. But if that does not, right, that is, let's say the target was here, so we cannot take another step of size whatever it was, right? It was n by 2. So since we cannot do that, from here on we will reduce our step size to half. Now we will take half the size, we come here, and then once more we cross it, so we are going to reduce the step size again. So that is how it is working. You can, if you try to visualize it, it is like you're trying to cover this distance, right? You're basically trying to cover some distance, and you try to cover it in some step like this. If you cross, then you don't want to do this, and you reduce your step size. If you cross again, you reduce it, and you will eventually reach it. So that's how this is working. And one more thing is that you will actually never need more than one step of some particular step size. And the reason is that any value, any value x, you can represent it as sum of distinct powers of 2. Why? Because it has some binary representation, right? And that is the sum of powers of 2, which are all distinct. So that is another way to think about this. Anyhow, this was another method which, if you like more, you can go with that. But if you don't, you can stick with the method I implemented. Another thing is, right now we are using arrays, so this index wouldn't really exceed the array bounds, sorry, integer bounds. But if we are iterating on some sequence which is not an array, which we'll do later, then usually I just prefer to use a bigger variable, bigger data type like long. Or another thing you can do is say low plus high minus low by 2. So this is the same mathematical expression. If you take 2 common in denominator and add, you will get high plus low by 2. But the benefit of this is that it will never exceed the value of high in any intermediate part. Previously we were doing this, so this part will exceed high, so it can go out of bounds, but this will never, right? Because we are subtracting. So yeah, that is another thing that is mentioned, not here but at many places. Now C++ is very rich in data structure algorithm related functionalities, right? So we have one for binary search as well. So if you want to binary search something, right? So if you have a sorted array, what we can do is try to find the first occurrence of a number, or a number that is less or greater than this. So what lower bound is, we specify it a range, so using begin and end, right? And then we specify a number, so let's say target. So target, let's say it is 11, right? So we specified a target, and now what it will return to us is a pointer to the memory address, right? Which is either equals to the target we have specified or just greater than this. So since we have specified 11, right, we will get the position at 11. However, if we now this iterator will actually not give us the position. To get the position, we'll have to do it like this: index, the starting index, because it is a pointer, right? So that's this will give us the pointer to some location. This is the starting location. So if we subtract, we will get what we'll get. We'll get the index. So this will give us the index. Let's see out the index. Now, as you can see, we got the correct index. Now, if we had given 12, okay, now 12 is not present, so it will give the first number which is greater than this. So we get 88. And if we specify something like 89, we will just get out of bounds, which is 10. Okay. If we were using the pointer, right? If we were using pointer, we will get equals to end. So element not found. And okay, what's the issue here? Oh, we have to remove the begin, right? If we are not subtracting from begin, then we get element not found because we got after 88. Now upper bound is similar. Just what it does is it does not return the first value which is greater than or equal to, but directly the first value which is greater than some element. So otherwise we can just print the index, right? So for 12 we got something which is the last element which is greater than it. And if we had 88, we will get no number which is greater than this, right? So we'll get element not found. That is how lower bound and upper bound works. Then there's also an equal range. So let's say you want to count the number of same elements, right? Sorry, let's say you want to count the number of elements that have some particular value, right, in this range. So one thing you can do is let's say count, right? Integer count. Find the first number which is greater, right? And then find the first number which is equal and subtract them. Then in that case, we will get the number of values which are equals to target uh, count, right? Again, why? Because so upper bound, let's say 88 starts here and ends here. They're all 88. Lower bound will give us this position. Upper bound will give us this. So this minus this will turn the number of elements. Now this will give us right 0. There are no 89, but there is 188, right? And for 4, we have actually two 4s, so we should get 2. Now there's a shorthand thing for this, not shorthand, there's another function, equal value, equal range. So this will just do the same thing for us. And okay, what is the syntax? So equal range. Hmm. This returns, okay, so what this returns is a pair of iterators. So the first and the last, the same things we will get from lower bound and upper bound, course, respectively. So what we can do is count dot second minus count dot first, and we'll get the number of elements. Now, it wasn't clear from this book, like how what they had done initially to me. So just to be clear, I searched CPP reference. So if you're ever unsure, just say search the function name and add CPP reference to it. You'll get this link and you can read this. Now I know this looks overwhelming right now. This is this template. If you learn template, you will understand what it is. Maybe I can teach templates in some other video. I've actually taught a little bit in my template video. Now template is my CP template, which is basically boilerplate code. So in that, I have actually taught how C++ templates work. So you can check that if you want. It is on my YouTube channel. Try to search it. Okay, I'll try to add the video link. Anyhow, that was that. Now, now let's try to have a look at what we are doing in a little bit more mathematical way. So these are the elements, right? So A1, A2, A3, so on. And the target is X. Now, whenever we check some index, what we are doing is we are comparing, right? Let's say that comparison function is F. So we are comparing some AI with X. And that gives us either less than or greater than or equals to. So this is what's happening, right? So now if we try to write this for every element, what we'll get? For the starting elements, we'll get something like less than, then maybe some equals, and then greater than, right? So basically, we are comparing AI is less than X or equals to or greater than, right? So less than. So initially, we'll get less than, then we'll get some equals, then we'll get some greater than. Now, this type of thing is what you can binary search. Okay. So it's not necessary to have a sorted array. You can have any sequence, okay? Any sequence. And if that satisfy a property, so if that uh, we define some function, okay, we have some function that with every element of the sequence, okay, it can be in any order, right? But they have to satisfy some property, and that would be the some sort of general sorting property, right? uh, if you don't know what general sorting property is, check out last video, but essentially they are in a relatively correct order, right, according to whatever property they are following. So we have some sequence which is in some sense sorted, and then if we enumerate this function that is defined by us for some target value for every element, and we get something like this, right? That may be false, 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 and then true, 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 true. Okay. In that case, we can binary search. Now, you might be wondering why isn't this like false, 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 then true, true, then false, false, false. Well, yes, but if you remember the second implementation that I did, where I did not check for equals to, you must have noticed that equals to and greater kind of act similarly, right? You will get some index which will either start from equals to or start from greater than. And that's exactly how lower bound works as well. So if less than means false and greater than equals to means true, then we have this sequence, right? False, 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 true, true, true. Then such a sequence can be binary search. Why? Let me explain. So we have false, 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 true, 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 true. If we check some place here, if this is false, I know that everything before this will also be false, so I can check the next, this part, right? And if I search here, I know that everything after this will be true, and I just need to check this. Okay. And this way I'll be able to find this edge where false to true happens. It just happens that in the case of finding a value in a sorted array, we get the case from less than, then transitioning to either greater than or equals to. And we are just able to manually check. If equals to is the case, then return element found. If greater than is the case, then return element not found. So yeah, and this is this is the type of sequence that for which you can apply binary search. So now, and this is exactly what we have been told here. If we have some function OK, which is our function which does the comparison over a sorted sequence, okay, over a sorted sequence, then if we write OK with that sorted sequence in X, and if it is like false, 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 true, 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 or true, 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 false, 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 because it is the same thing, right? If you get a function result like true, 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 false, 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 then you can just change the function definition. You don't even have to change the function definition. You can just have the same idea that if it is true, just change the driving a little bit different. If we get true, we go to right. If we get false, we go to left. That's just the opposite. So yeah, binary search can work on any of this. So now let's see if they have told anything else. Yeah, let's actually talk about the time complexity. So time complexity is very simple. Initially, we have an array of size n. After one check, it becomes array of size n by 2. After another, it becomes n by 4. After another, it becomes n by 8, and so on. Since there is only a simple check per step, it is O1. And how many steps are there? There are log n steps. Check out previous video why it is the case. I explained in the merge sort section. So time complexity is log n. Now, if in the check function you are doing something more, so let's say its time complexity is some k, right? Then time complexity would be k log n. Okay. So that is that. Now, what is this? Binary search function. First increasing, then decreasing. Okay, so this is actually ternary search done via binary search. So right now, what was the function we had? Let's have a look. The function we had was, it is false, 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 and then true, true, true. Right. Now we're gonna look at a different type of function, which is a quadratic function really. So if it is increasing and then decreasing, or decreasing and then increasing, then if we want to find this peak, how can we find it? Now there is a ternary search algorithm. You can search CP algorithm for that to see how that will work, but it is just an extension of binary search. We check 2 points at n by 3, n by 3, and then we compare. Based on them, we figure out what is the next partition. For example, let's say if both of the lines came here, both of the points came here, and they are since they are in increasing order, we will know that peak will be here. So yeah, that would work similarly. If it is like this, right? If this is not there and it is decreasing, right, like this, then we know that this is the search space. And if it is like this, then we know that this is the search space. Now you can actually use this idea and always have one number here and the other just after it. Okay. And now If they are in increasing order, then that means the peak is to the right side. If they are in decreasing order, then that means the peak is to the left side. Right. So yeah, and then eventually we'll reach this where one of the elements you will choose will be the peak. And this is the implementation that they have shown. Now, if you didn't understand it, do not worry about it. Ternary search is a little less used. And after you've actually practiced a little more binary search, only then I actually recommend to bother about ternary search. Another thing about ternary search, whenever you're using that, is that this has to be strictly increasing, right? And then it can have multiple peaks, and then it has to be strictly decreasing. Why? Because notice how we check, let's say, some I element and then I plus 1. So if they are equal, then we will have no way to ascertain where we are. So that is something you have to keep in mind. And if you don't like this type of implementation, you can say ternary search integers code forces, and you'll get a sweet implementation, which is this. And yeah, okay. So ternary search, I actually did not plan to do it, but I just noticed that we had ternary search here, so we just did it. Now let's talk about uh, an extension of this. So let's take an example for this. Okay, this FFF So I say that it can work on any sequence, right? So let's take an example where we are given two sorted arrays, right? We're given two sorted arrays and we want to find the uh, the median of their combination. So how can you find that? There's one way. You can just combine them, right? In O and N, right? If it is N and this is M, so O N plus M, and then do a binary search. So that would be N plus M plus log N plus M, which is N plus M just, right? But we can actually try to do it faster, and I'll show how. So notice that what we want to find the median, and the median, the thing that we want to find is actually a sorted sequence. The median could be 1, 2, 3, considering they are positive integers. So 4, 5, up to infinity, right? Or whatever is the maximum among them. So I'm just going to call it A max. Now, this is the sequence of possible medians. And now notice that they are sorted. Now, let's see if we can actually apply binary search here. Well, of course, if if x is not the if x is less than the median, right, then we don't have to check from 1 to x and just have to check the next part. But can we check if it is a median, right? So there are two steps. First of all, have a sorted sequence, right, for our value that we want to find, which is the answer, right? Our answer is the median. So this technique which I'm teaching you right now is also called binary search on answer. So we are binary searching on the answer, which is a sorted sequence, right? So we can binary search on it. And now we just want to ascertain that this check can be done in feasible time, right? So how can we check if it is less than or greater than median? Well, I can check how many numbers are less than this x in first array using the lower bound, right? And in the second array as well using the lower bound. And if it is a median, then the number of numbers that are less than the number, the median, has to be equals to n plus m by 2, right? So with one binary search, I can check how many numbers are smaller than my current x here and how many are smaller than current x here. So P and Q, right? So P and Q. Now, now what? Now what? Now we just need to check that this P plus Q has to be greater than equals to n plus m by 2, right? Nah, it has to be equals to n plus m by 2 because that is the exact amount of elements we want less than, right? So we can find P plus Q, and if it is less than n plus m by 2, right? If that is the case, then we try on the right part of our search space, which is whole integers, right? If it is greater, then we try on the left part, and if it is equal, then we have found it. Actually, no. So here's the thing, right? Binary search, like I said, it really works for this property, right? You, I'll show you the caveat here. So let's say median is 9, right? All the numbers before it were less than equals to 5, and then all the numbers after this are like less than greater than equal to 10. Now, when you will be checking for median, even if you check for 6, you will get what? You will get great. You will get 5. What is, let's say k numbers are less than and k numbers are greater. You will get k numbers less, but this is not a number in the array, right? So while it satisfies the property, it's not actually a median. So what we actually try here, right? We try to find the maximum value which satisfies this constraint. So it will be like, uh, so if we try 6, we know that it is greater than, okay, this was k, right? So we know that it is greater than k elements. So now we will check here. We will not check for equals because equals can give us the wrong answer. We'll just check for greater. And if we just do that, if we land ever here, we will just reduce our search space, right? We will discard those, and eventually we will land in this 6, 7, 8, 9 space. And if we keep continuing this, we will land here. So whatever is the bigger value, and if let's say it was greater than 12, right? 6, 7, 8, 9, 10, 11, 12. Notice that they will give us the correct answer. They will not because they are greater than 9, right? So we don't have to worry about that. So that is how we solve the problem. I'm going to want you to implement it yourself. That would be your homework for this video. And try more binary search questions. Binary search is one of the most important topic in CP. It is just the most important topic, really. You can solve a lot of problems with binary search. So hope you like this video. If you did, leave a like, subscribe. Make sure to practice, and I'll see you next time when I'll release a video.